Determine the internal normal force, shear force, and bending moment in the beam at points C and D. Point C is located just left to the roller support. Assume the support at B is a roller and A is a pin. To solve, first of all, let's convert our uniform distributed load into point load. So in this case, we're going to have two different loads, one for the rectangular area that is still 9 kilonewton, and then the other one for the triangular part from 9 till 18. For the first part, it's simply going to be 9 times 9, which is 81 kilonewton. And for the other, it's going to be half times 9 times 9, which comes up to be 40.5 kilonewton. Now we can find our external reaction forces. So one is going to be at B, and there's going to be horizontal and vertical at A. Horizontal will be 0 because of no other reaction force acting on it horizontally. Okay, now we can take a moment about the point A. We're going to have 40.5 kilonewton, and it's clockwise, and it's going to be one third of the length of the beam from A. So this case will be 3 meters. Then we have the clockwise 81, and it's halfway, so half of 9 is 4.5 meters. Then we have our BY, which is counterclockwise, and it's going to be 6 meters away from A, all equals to 0. Solution for BY comes up to be 81 kilonewton. And by inspection and taking equilibrium moment along the y direction, we know our AY is going to be 40.5 kilonewton. Now we can draw the free body diagram till the point D. So that's where we're going to cut our beam going from the left hand side. So we're going to have our AY, which is 40.5 kilonewton. And then we have our 40.5. I mean, it won't be 40.5. We'll have to use proportionality to determine that value. We'll leave that for now. But then coming down to the cut, we're going to have our shear, our normal at D, and then our moment at D. And now for the conversion of our uniform distributed load into point load. So our first load is simply going to be the 9. So for that 9, we're going to have, it's going to be halfway, so 1.5 meters away from D. And it's simply going to be 3 times 9, which is 27. Pardon me, I made another mistake here. We actually don't know the height of the triangle cutoff at D yet. So first we have to find that. So that means we're going to use proportionality. So we know it's going to be delta initial and delta final. We're going to have, first of all, nine take away 18 kilonewton divided by 9 take away 0 meters equals to unknown W, or in this case I'm going to call it F, take away the 18 divided by 3 meters take away 0 meters. Solving for F, we get our solution as 15 kilonewton per meter. Now we can use this 15 times 3, so that will give us 45 for our rectangular portion. And then for our triangular part, it's going to be 15 take away 18, which is 3 times half times 3 gives us 4.5 kilonewton, and this is going to be 1 meters away from E. Alright, now that we have this done, we can start solving for our shear at D. So our shear is going to be simply sum of the forces in y direction, or we can say vertical equilibrium equation. We're going to have our shear, which we don't know yet, negative 45 kilonewton, negative 4.5 kilonewton, and then positive 40.5 kilonewton, all equals to 0. Solving for shear at D, we get our solution as 9 kilonewton negative. So this means we need to convert either our sign or just right here that it's going upwards. Then our normal in this case is going to be 0 because there aren't any other horizontal force acting on this beam or structure. And finally our moment. For moment we just have to take moment about the point D. So in this case we can have counterclockwise moment at D, and then counterclockwise 45 kilonewton, and it's 1.5 meters away from D. Then counterclockwise 4.5 kilonewton, and it's 2 meters away from D. And finally clockwise 40.5 kilonewton, 3 meters away from D, all equals to 0. Solving for moment D, we get our solution as 45 kilonewton meter. This means our assumption for moment D is correct, that it's counterclockwise. Now similarly we can move forward to point C, and we were told that point C is left of point B. There are two ways to solve this. We can either approach it from the left hand side or the right hand side of this beam. We're gonna try to approach this particular beam from the right, even though we usually don't do this, just for the experiment purposes. Okay, so first of all, let's draw our free body diagram. From the right hand side, so we're gonna have by right at the cut. Then we know we have our shear, our normal, and finally the moment. We also know we have a distributed load, which we'll need to find through proportionality. So this time we can have our negative 9 take away 18 kilonewton divided by 9 take away 0 meters. But because we are approaching it from the right hand side, we'll have to flip the values a little bit. So in this case, we're going to have to have it something like this. So it's going to be 18 kilonewton take away 9 kilonewton divided by 9 meters take away 0 meters, because we are assuming right as the beginning point or the initial point. And then for the final, we don't know what the value is, but we do know that our initial value is 9 kilonewton divided by final will be 3 meters away, and initial is 0 meters away, all equals to 0. And solving for value F, we get our solution as 12 kilonewton per meter. So using this 12, we know that first of all, we're going to have our rectangular load, which is simply going to be 9 times 3, which is 27. Pardon me. Yeah. It's just going to be 27. 9 times 3 is 27. And then our point load is going to be 12 take away 9 times half times 3 meters, which comes up to be 4.5 kilonewton. The 27 portion is 0.5 meters away, and 4.5 kilonewton is 1 meters away from the cut or point B. And we have already found the value of Py, which was 81 kilonewton. Now we can sum the forces in y direction to find a value for the shear. We can have our shear, then our 81 kilonewton, then our 4.5 kilonewton going downwards, and same for 27 kilonewton, all equals to 0. Solving for shear, we get our solution as negative 49.5 kilonewton. Similar to our initial or the problem before it, we know there is no horizontal reaction force, therefore normal is 0. And to get our moment at C, we simply have to sum the forces. So we're going to have clockwise moment C, then we have clockwise 4.5 kilonewton times 1, and then clockwise 27 kilonewton times 1.5 meters, all equals to 0. Solving for moment at C, we get our solution as negative 45 kilonewton meter. This means moment C should be counterclockwise.